While it seems that we've covered all the possibilities, occasionally we get a solid that's not like the rest, that doesn't fit into the other categories. These exceptions have unusually high melting points, which indicate extremely strong forces between the units. Turns out that these materials have a network of covalent bonds between the units throughout the structure. We call them covalent solids or network covalent solids. Be careful with the terminology. Covalent compounds and covalent solids don't always go together. If we look at the melting points of some of the second period elements, one of these is not like the others. Nitrogen, oxygen, and fluorine all exist as diatomic molecules with dispersion as their only intermolecular force. Of those three, we would actually predict the trend to go in the other direction based on mass, but the masses and melting points are so close to one another, perhaps we shouldn't draw any conclusions about them. However, carbon at more than 3,000 degrees C must have a force that is much stronger than dispersion in the solid state. It turns out that stronger force is a covalent bond. Here is the structure of graphite, shown as a sheet of carbon atoms. Looking at an individual atom in the ball and stick model on the left, it is part of three different hexagons. This would appear to be an sp2 carbon with 120 degree bond angles. Although harder to pick out in the space-filling model on the right, you can still find the hexagonal arrangements. Single sheets like this, which is called graphene, have only recently been discovered and have remarkable strength, conductive, and magnetic properties. Graphite has these sheets stacked on one another. While individual sheets are very difficult to break apart, one sheet is not that strongly stuck to the next. You can mechanically scrape one sheet from another, like you do when you move a pencil across a piece of paper. Note that you're not just leaving one sheet of graphene on your paper. You're removing chunks many, many sheets thick. This hexagonal arrangement is also seen in carbon nanotubes that have interesting conductive properties. Here is the structure of a diamond. Locating one of the carbon atoms in the body of the cell, we note that it is bonded to four other carbon atoms with 109 degree bond angles. This is another unit cell based on the cubic structure. We can locate atoms at the corners of the cube, on the faces of the cube, and three more in the body of the cube. Here is a different unit cell called zinc blende. It is based on the structure of zinc sulfide, where the zinc atoms are shown by the gray spheres and the sulfur atoms are shown by the yellow spheres. Note that the sulfur atoms take the body positions, while the zinc atoms take the corner and face positions. You may be thinking that with zinc, a metal, and sulfur, a nonmetal, this should be an ionic compound. This is a case where the electronegativities are not that different, so there is a considerable amount of covalent character in the bonds. And characterizing this compound as having covalent bonds rather than ionic bonds is reasonable. Finally, we show the structure of one form of silicon dioxide called beta cristobalite. Silicon atoms are shown by the gray spheres and are at the same positions in the cube as the carbon atoms in diamond. But notice that we cannot identify individual SiO2 molecules. This silicon, highlighted in the body, is bonded equally to four different oxygen atoms rather than just two. The unit cell stoichiometry will have twice as many oxygen atoms as silicon atoms, but individual molecules are not present. We return to our chart one final time and can now add our fourth solid type. Notice that elements in covalent compounds can both be network covalent solids, but they can also both be molecular solids. This is a point we will need to come back to on a subsequent page. In network covalent solids, the unit is again the atom. We cannot locate molecules in the structure. All atoms are held together by covalent bonds, so there is no longer the distinction between forces inside a molecule and forces between molecules. There is a network of bonds.